continue to the last lecture. Space charge and junction capacitance. We know the capacitance is generally can be written as phi over phi I minus m. Right? What we are talking about here is when we have junctions, emitter base, and the same thing can be taken for the base and collector, of course. And then in this space charge region, let's say we have M plus and P minus emitter and base. And we certainly have Xn and Xp, the space charge region here. And then if the doping level has a considerable difference in the doping levels, then we know the space charge region also shows a lot difference. So the total space charge region can be approximated to the Xp if the Xp is the doping level of the base is very lower than that of emitter, right? So we can think of this as a capacitor with the two metal plates separated by the space charge region. And that capacitance can be defined something like this. And here the J phi is Q epsilon ND and A 2 phi I and D plus NA and plus M. And if it is a step junction, the M is equal to 0.5, and the built-in potential phi I is going to be Na over Ni squared. This thing we have discussed the last time. Now, of course, if we have a heavily doped N plus and lightly doped base, this thing can be simplified with that. Like if Na can be neglected, and then this whole thing, this is going to be cancelled, so that the whole capacitance C J phi is going to be a orderly function of lightly doped region. Okay, so the lightly doped region is really important in this capacitance. Now, the charge is going to be can be obtained by integration of two voltages and then 1 minus 3 over phi I minus m dV, of course. And then if we do the integration of this equation, we end up with minus phi I 1 over 1 minus m and 1 minus v over phi I, 1 minus m, v1, v2. Things like that, okay? So we can determine the emitter charge, which is going to be integration between the 0 volts and the emitter base forward bias, phi I VE minus M VE and dV. In the same token, we can set the charges in the space charge region of base and collector like this. BC minus M BC dV. Okay, so these two terms are the space charge which this depletion regions is going to be modulated by the applied voltage VBE and VBC. This space charge region is going to be modulated. It's going to be widened and narrowed depending on the voltages, right? With that change in voltages, we can have a capacitance. And that capacitance, if you integrate along the voltage, then you can get the charges corresponding to the voltages applied between base and emitter and base and collector. So these are the charges for the junction capacitance. And we have another charges which coming from the minority injection charges. Injected minority carrier and diffusion capacitance. The stored minority carrier charges is going to be Qn, Qa, and P naught e to the V over minus 1 Ln. And the Qp and the base is going to be Q and Pn naught e to the V over Vt minus 1 Lp. Okay, we have seen this, and what we are talking about is in the emitter and base, we have some stored charges, and something like this. The minority carrier is going to be injected to the base with the application of the emitter base voltage, and also the hole is going to be injected to the emitter. So we have some charges which has been injected to each side of the diode as a minority carriers, and then that charges is going to be written something like this. We have covered this in the diode section, right? And we can set the characteristic time, characteristic restricted time such that the current is going to be expressed on the characteristic time tau. So we just define, we know the charges and we know the current with this minority carriers, and then we can deduce this characteristic time which is corresponding to this equation, right? So we have been written that the charge is there, and then we are going to write about the current, which we covered on the diode section. The IN is going to be QA dN over Ln NP naught e to the Vt. This is thermal voltage, and IP is going to be QA dP over Lp Pn naught e to the V over Vt minus 1. Okay? Then, according to this equation, now we can set the characteristic time for the whole, which is going to be Q over I. You just to put this current and the charges into this equation, which is obviously not a hard thing to do. T minus 1 over Q A dP Pn naught into Vt minus 1. Okay, then it's going to be written something like this. Now, if we can get the characteristic of time, then we can set the diffusion capacitance. That is dq over dV. The same thing for the capacitance again. And then all we have to do is we have to make a derivative of Q with respect to V, and then we end up with QALP Pn naught e to the V over Vt minus 1, and that is Q over Vt. Simple. That's the characteristic of the exponential, right? And the charge is now going to be written like this. So dq over dV, which is diffusion capacitance with this injected minority carriers, now going to be one over Vt I and tau p. So we have two capacitance which are the space charge capacitance and this diffusion capacitance. And if you plot that, plot the charges with respect to the forward bias between emitter and base, you can see that with that equation it says QVE is going to be space charge is going to vary something like this with respect to the application of the emitter and base voltage. On the other hand, that minority carrier diffusion charges is going to change somewhat, something like this, QF. So which means at the beginning of this, at the small amount of emitter base voltage for the voltages, this is going to dominate of the total charges stored at the bipolar device, right? But as this emitter and base voltage increases, this minority injection charges is going to increase exponentially, drastically, so that at the high emitter base voltages, this injected minority carrier charges is going to dominate the whole stored charges in the device. So the next thing we're going to do is we're going to develop a charge control model. We have covered this in the Evers model a little bit, but this time we're going to talk a little bit more detail on that. Charge control model. The objective. We want to get terminal currents IB, IC, and IE, these terminal currents, with as a function of charges or the change in charges. Okay. How to do it? The method. We want to get the charges on the base, emitter, and the collector, and reverse biased base charges. We have two charges for the base. One is the forward biased emitter base charges, and the other is the reverse biased emitter base collector charges. Okay. And then the next step is we want to express this whole thing only two terms, QF and QR. And for that, we want to use the approximation for this. And then we are going to use QF and QR in the QVE, QVC. This is the minority carrier injection charges, okay, for IC, IB, IE, the terminal currents. So we're going to follow these three steps. And the first thing, we have driven this, as a matter of fact. Okay. The first thing is QE is QA EPN e to the V BE over VT and something like this. That is the charges in the emitter. And for the base, forward biased base charges, we have a forward bias between emitter and base. And for that part, we can write something like this. E to the VBE over VT e to the XB. Okay? And IC is just the derivative of the delta P with respect to the distance. That is going to be NP e to the VBE over VT. And that is going to be QBF over XB square over 2DN. Okay? As by definition, it should be equal to QBF over tau B, so that tau B now is nothing but 2DN. You can write this fashion, right? And IBF, we can do the same thing. We could derivative of that, and QA dP Pn e to the VBE over VT. Okay, and this thing is XE square 2dP, and that is Q E over tau E by definition, so that now tau E is nothing but 2dP. Now the important approximation that we have to make here is, since it is a forward bias between emitter and base, and we have very heavy doping on the emitter compared to the base, we can make the charges in the emitter and base in a forward bias case can be approximated to the QBF, because QE is much smaller than the QF. Okay, and then we set this QF. And see, the collector current has to be defined like the charges divided by the characteristic time, that we define the characteristic time in this manner. And now we have tau F is going to be approximated to the dN, which is exactly the same to the tau B. Okay? And define tau BF. This is a new definition. Okay? Tau BF, and we just define this tau BF as QF over QE. We know QF is much greater than the QE, and the tau E, we define the tau BF in this manner, and then we can set tau F is going to be IBF times tau BF, so that tau BF now is going to be beta F, the gain, and the tau F. So the relationship between the tau F and the tau BF, which is new definition, these two characteristic time is going to be related with the gains beta F. Okay. So this means what we have done there is we have space charge region between emitter and base, and the space charge region for the base and the collector, something like this. And then we know we have very small amount of QE, which is coming from the hose from the base to the emitter, and we have injected QBF, which is large compared to the QE. We just put this situation into this simplified model, like we just set QF. So we add these two things into one QF parameter, and then we want to set IBF and the collector current IC just in terms of the QF by utilizing the facts that the characteristic time is related with these parameters, something like QF over tau F, okay, and then IBF now is going to be QF over tau BF. That is a simple equation. That is a simple form. We just use tau BF, a new number, a new characteristic time, in order to set these equations. And then we can develop the each characteristic time to make this thing possible, and then we end up with these equations between the tau BF and the tau F. All right, so far we have discussed about the forward biased emitter and the base. We do the same thing, exactly the same thing to the base and collector, which is a reverse bias this time. And this time, what we are going to have here is, this is the base, and this is collector. Now we have QBR, reverse bias, in the base, and then QC for the reverse bias, the collector. Okay? And then this can be simplified just to one QR with the approximations. Now we want to lump everything, QBR and QC relations, to the QF, QR, it's a reverse bias. So now this is the QR. And then we want to set this emitter current and the base current, reverse biased base current, with this QR charges. And then if you do the same thing, just similar to the ways that we have developed for the emitter and base, we end up the equation something like this: tau R and IBR now is QR over tau BR, and tau BR is going to be LP square over DP, and then that is beta R tau R. Okay. The details of this derivation is going to be on the text. So you just refer to that, refer to the text to find out the details for the derivation of this equation. But you realize that the derivation of this equation is just almost the same to the derivation that we have done for the emitter and base case. Okay, just this is the forward bias and this is the reverse bias. So as a total, what we are going to have is we have 4 terms here. One is the current for the collector or the emitter, and we have some current coming from the base, and we have current coming to the collector. Okay, and then we can relate this things with 2 charges here, and then this thing is going to be QF or tau R F minus QR over tau R, and then this is QF over tau F BF, and this is QR over tau BR, so that we can develop the equations. The IC collector current is QF over tau F minus QR 1 over tau R plus 1 over tau BR. And the emitter current is going to be QR over tau R minus QF 1 over tau F 1 over tau BF. Okay? And IB is QF over tau BF plus QR over tau BR. Now, if you take into account of the time-dependent terms, then what you have to do is you have to add, okay, this is the things that you have in the DC charge control models. But if you have a time-dependent term, time-dependent terms, then it means that you have to add the capacitor, okay, which is a QVE, the minority injected charges, QVC, onto this terminal here. And also, you're going to add the charges in this space charged region. So, if you have to think about the time-dependent term, this is a DC model. But if you have to think about a time-dependent term and a switching mode, then you have to add these charges that we have discussed earlier in this lecture. The charges related to the injected minority carriers and the charges stored in the space charge regions, each of those. Okay. So now the equation is going to be, now if you think time dependent terms, base current, then you just have the DC term here plus dQe f over dt and dQr over dt, and then dQ VE over dt, and then dQ VC over dt. In reality, this among these terms, some of the terms are going to be very large compared to other things, so that in reality, this the equation is not going to be this complicated. IC is IC, the DC term, minus dt over dQr minus dt over dQVC. And IE is IE minus dQf over dt minus dQVE over dt. Okay, so we just developed the charge control model of the bipolar device, and next week on Monday we're going to discuss about the saturation mode. So far we have discussed about the bipolars working in active mode, which is you put the forward bias between emitter and base and reverse bias between base and collector. That is going to be called active mode. And in that active mode, this charge control model is going to be developed according to that. Of course, if you change the bias, you can have the same thing, but in a bipolar device, if you have a forward bias, for example, which is exactly the same thing to apply reverse bias, in that case, on the base, you are going to have a saturation mode, which is a little bit different from this. Okay, and then we are going to talk about the saturation mode and next week on Monday, and then we wrap up the bipolar device sections. And after that, probably we go back to MOS transistors, and we're going to discuss about the special structure of MOS device. And if we have a time, we are going to discuss about the gallium arsenide as well. Okay? So have a nice weekend, and we'll see you on Monday. Good.